Thank you for the introduction. Today, I'm going to talk about, as the title says, ambient artificial intelligence, bringing artificial intelligence to IoT devices like around you. There are so many IoT devices around us, right? So let's talk about ambient AI little by little. And actually, this ambient AI, I'll try to give you a very high-level description on ambient AI so that your audience who are maybe not familiar with this field, especially our dear freshmen, can understand easily. And actually, the term ambient AI is kind of new, which Professor Sang-Kyun Cha made 2 years ago, actually. But its concept intrinsically, it does not come out of nowhere, but is closely related to a long history of our computing paradigm. So let's see how this history has come so far. So from 1960 to 1980, a computer looked basically like this. Basically, a gigantic workstation in a machine room was a single computer, right? Single computer. And workers in an office room without their own computers just have I/O devices for typing and printing. Then multiple workers remotely access the workstation through intranet. Yeah, intranet is a small local area network which is very different from internet that connects all over the world these days. So in that period of time, the main computing paradigm was on the server here, right? Oh, let me enable pointer here. Server here. But sharing remote servers together is, as you know, it's not at all convenient. I myself want my own computer, my own personal computer, right? Rather than accessing remote server and sharing the same computer together. So from 1980 to 20s, to solve the problem, small personal computers emerged, Apple, and more people started having their own computers, not only in the office, but also at home. And thanks to these personal computers, people do not have to rely on this remote server anymore. So at that time, the main computing paradigm was at the edge rather than the server. So now in the 21st century, another very big thing emerged, which is now internet. Yeah, internet built on famous TCP/IP standard. As more and more computers around the world are connected to this internet, a lot of data could be gathered from these numerous computers. And this numerous data is called big data, a coined term, right? And that's then what's the problem? Yeah, gathering big data is a good thing, but yeah, now you see this red colored a huge workstation, right? This gigantic server is no longer enough to process and store all of the big data because data is too big. And to solve the problem, computing technology stepped forward so that multiple server computers could collaborate together, which result in, as you can see here, cloud computing. Now we have a data center, as you can see here, comprised of a number of server computers that process and store data in a distributed manner. So in that period of time, the main computing paradigm went back to the server here, right? And next, lots of smaller computers, as you can see here, such as tablets, smartphones, smartwatches, and smart speakers were developed. And as data sources are increased and diversified, the servers gather even more data. You can see these thicker red lines, right? In this environment, like big diversified data environment. This cloud computing, yeah, is still powerful, but there are some problems now. These three problems. First, since many data that these small IoT devices gather are private, sensing some private information around people, right? And delivering the data through the internet and storing and processing the data at a third-party server causes significant privacy leak. You know, if you send your private information to Google Cloud, that means Google knows your private information. Also, communication vendors such as KT and SKT, yeah, as you might know, yeah, have countless private information, including they actually know what kind of words you are searching through Google. And second problem, yeah, there is a new need on the application side. Users now want to enjoy real-time applications like games, such as augmented reality and virtual reality. But if data is sent from the edge devices to the server located very far away, and sometimes even across the ocean, right? And processed at the faraway server and come back to the local edge devices, this round trip end-to-end response time is too long to enable real-time services. Third, if you depend on the server computing too much, then once your precious internet goes down, disconnected, then all your intelligence and wonderful services, unfortunately, it will disappear together suddenly. So many people are using Overleaf these days. Yeah, you guys might be using it too for writing papers or reports, which is great. But on the flip side, if you lose internet connectivity, you cannot open any of your document at all. Basically, you will become simply dumb without internet connectivity. If you imagine that all smart devices in a factory, very important factory, lose their capability depending on internet connectivity, it will bring a disaster, right? So what could be a solution? Yeah, you see this term, right? Computing on the edge devices directly. Although edge devices are much more resource constrained compared to the server, they can still do decent amount of computing. But just to clarify, the advent of edge computing does not mean, oh yeah, now let's forget about the cloud and just rely only on the edge. This is more about utilizing both cloud computers and edge computers together synergistically. So in summary, people mainly focused on the server first and became more interested in the edge, and the trend went back to the server. And finally, these days, we need to utilize both server computers and edge computers together, which is called computing in continuum. So you guys might be wondering, why did I talk about computing history? So this is because evolution of computing technology directly impacts AI paradigm. So from now on, I'd like to talk about three important pillars of ambient AI based on this figure. The figure shows three computing tiers, including cloud, edge, and very, very resource-constrained IoT devices together. So the first pillar is very famous pillar, machine learning and deep learning models that are built on the powerful cloud infrastructure. So you can see red box on the highest tier, right? And in terms of pure algorithm, as you can see here, the net was developed way before 21st century, actually. So let's take a look at a video clip just for fun. Let me click.
What's it like to learn science on Brilliant? Brilliant gets you hands-on.
That's an advertisement. Yeah. So you guys use MNIST data set to classify numbers when entering into this deep learning regime, right? And the video shows that the number classification was successfully done like 3 decades ago. And you see, yeah, all the successful classification here. And it was in 1993. Yeah, and you can see all this happy grad school student. Maybe your future, just for kidding. Yeah, but unfortunately, even with this wonderful algorithm, it was AI winter, second winter, right? At the time, it was AI winter, not because of lack of algorithms, but due to lack of useful big data sets and computing infrastructure. It is great to classify numbers, but they are much more valuable and useful tasks to do in the world, right? So, but people realized that to do something more useful and valuable, it is not at all easy to gather, store, and process enough big data. So note that it was the era of personal computers at that time. Then what happens? Cloud computing emerged. Google TPU, NVIDIA GPU, and Amazon AWS, Microsoft Azure, and Google Cloud, and wonderful software platforms such as PyTorch and TensorFlow were developed. So all these hardware and software became infrastructure to store and process big data. And then what happened? ImageNet in 2009. So now not only big data computing infrastructure, but also benchmark big data set are provided. So with the help of computing infrastructure and big data set, now people were able to revisit deep learning algorithms. And representative milestone work, AlexNet, came out in 2012. And AlexNet surprisingly shows that deep neural networks outperform light machine learning models, which have very careful feature engineering from computer vision experts. So from that time, deep learning has significant attention, has received significant attentions. And let's move on to the second pillar, which is the Internet of Things on the lowest computing tier. Yeah, so at the end of 20th century, there was a really ambitious project called Smart Dust. I mean, not smartphones, smart speakers, but smart dust, You can see how ambitious it is, right? So its vision was to make a small computer, as small as dust, that has all the computing, sensing, and networking capability. Well, yeah, as you can see here, this device was kind of too big to be called dust, and performance, as you can see here, was not that great. Yeah, too slow clock and too small RAM, too slow networking speed, but it worked in some sense, and it brought a significant paradigm shift, actually. And yeah, one of the leading professors in this project is Professor David Collar, whom Professor Cha just mentioned, and he is my postdoc advisor. And this is our group picture, and this is me. So which explains why I am in this field. And these small devices were used for gathering information, mainly, not like processing or AI computing directly, just sensing something and delivering. So basically a number of these devices are scattered in a target area, And these devices are powered by battery, AA or a coin cell. Then they are expected to sense what's going on nearby. Then deliver information wirelessly to the server, and they should survive for years. So they are for remote monitoring. People were very inspired by these small devices, and lots of smart people went to the wild and deployed these IoT devices for remote monitoring. Let's see some example. Uninhabited island, wildlife monitoring zebra, and volcano even, and bird nest, redwoods, bridges, hospital, and markets. This work is what I did. Basically, a lot of smart grad school students just went to the wild and deployed and do all the practical stuff. And for the last 2 decades, small edge and IoT hardware have evolved much further, including now low power AI accelerators. Yeah. Now we see the term AI here. And this chip is very small. It's smaller than a cent, right? And you can see HoloLens here, smartwatch, smartphone, and also Google Core devices, which have its own edge TPU, and NVIDIA Jetson series that has its own mobile GPU. And you can see not just TensorFlow, but TensorFlow Lite, right? And these days also there is another version of PyTorch called PyTorch Mobile. And actually even lighter version of TensorFlow called TensorFlow Micro. There are a lot of lighter versions of software platforms. And there are even embedded microcontroller for AI computing called Cortex M55, developed by ARM. So now we have smart something, a lot of smart something, right? Smartphones, smart speakers, and smart watches. And then naturally, this question comes up. So given that we have a lot of smart something, why don't we use them more smartly in the context of AI, rather than just relying on the cloud, right? This question leads us to the last pillar, naturally, which is edge computing. So in 2009, one seminary paper on edge computing was published, which is about cloudlets. Kind of funny, it's not the cloud, but cloudlets, a piece of cloud, right? And the idea is when a mobile application on a smartphone needs intensive computing, then how about using nearby Wi-Fi gateway, because it has kind of powerful computing capability. And it is also called cloudlets, not the cloud. And using this Wi-Fi gateway would be more helpful than using this faraway cloud mainly in terms of latency, right? Because the Wi-Fi gateways are much closer than the cloud. So it results in faster response. But these resources are much more constrained compared to the cloud, so it is called cloudlets. So from that time, lots of edge computing paradigms have emerged, such as fog computing, dew computing, and mist computing. Basically, whatever between the cloud and the land, right? They are slightly different, but mostly similar. And finally, I want to conclude this chapter by saying that ambient AI is at the intersection of all the 3 pillars I've mentioned: AI models, IoT, and edge computing. And although cloud-based AI is very powerful, it is very true, as I said before, ambient AI is still needed to enable next generation AI application that require more intimate interaction with users, real-time interaction, and need that the applications may need to process more private information, including sensing information, right? So for better privacy and better responsiveness, processing AI computation directly on the edge devices will be very helpful. And because of its usefulness, there's some hype about this field. So you can see from this Gartner curve, there are 5 stages of a newly emerged computing technology, and embedded AI is on this stage, second stage, which is called peak of inflated expectations, right? So expectations are inflated. So it has to show some practically working samples and examples in real applications, but for now it is on the second stage yet. So that means there are many challenges, technical challenges to investigate and overcome, which will be very interesting. With that, let's switch our gear to research topics about challenges and some solutions and research field. So the first one is application-oriented AI systems. So on advantage of IoT devices is that they can generate various information using servers. Some of them have speakers, some of them have microphones, some of them have some wireless devices, some of them has cameras, various sensors. So it is worthwhile to investigate what kind of information is good for a target application once you get some target applications. So for example, you may be able to get 2D images from an RGB camera and 3D point clouds from RGBD camera, LiDAR sensor, or radar sensors. Or you can sense motion information using vibration sensors, basically accelerator, right? Accelerator. And the sound, you can also catch sound using microphone and electric current, and even wireless signals like Bluetooth signal or Wi-Fi signal and so forth. So given the various types of information, fusing these heterogeneous data will be also an interesting topic to result in some useful application result. And another area is deep neural network lightning. Yeah, this is an interesting figure. So as shown in this figure, state-of-the-art deep learning models are getting bigger and bigger rapidly. And yeah, if you see this transformer example, yeah, the training burden for transformer models increases 750 times for 2 years, which is huge, gigantic, right? This is too much, maybe. So AI Atheist at Google published a paper that warns the danger of making deep learning models too big, in terms of in the perspective of environment, right? Environmental perspective. This is an inconvenient truth, right? It's some dark side of this fancy AI models. And you know what? These researchers got fired from Google while working on this topic. So I want to mention that there's also another direction of deep learning research, which is not just scaling, but lightening a model for resource constrained devices. You can see that these devices yelling, AI models are too heavy for us to process, right? So there are multiple different hammers to lighten a deep learning model. The first one is quantization. So quantizing model weights and also activations from real numbers, 32-bit floating point real numbers, to integers. Sometimes 8-bit, sometimes 16-bit, sometimes even a binary number, only 0 or 1. So very surprisingly, even with these binarized weights and activations, the accuracy for simple tasks is not degraded. And this field has evolved significantly for the last decade. And another hammer is weight pruning, which is cutting trivial edges. Edges are weights, and trivial edges to reduce model complexity. So cutting an edge basically means simply nullifying the weights. So just make the weights value to 0. So it does not degrade accuracy very much once the edges are confirmed to be trivial, right? And there are a lot of different classes of pruning techniques. Just node by node pruning and channel wise pruning and so forth. And third one is actually very powerful and very popular these days, which is called knowledge distillation. The idea is that if there is a heavy but well-performing model, maybe ensemble model, which is called teacher model, then a small model called student model can distill knowledge from the teacher model without mimicking or quantizing the original weight, but with a totally different network architecture. They just focus on the output. So input-output matching of the teacher model. They just want to mimic that match. And this technique successfully reduces even a notoriously heavy language model called BERT, transformer-based model, enough to run even at a smartphone. So it is called mobile BERT. So yeah, transformer is heavy, it is true, but with some techniques, you can run it at even edge devices. And next topic is lightweight execution. So we assume that we have a well-performing deep learning model. So it is not about training or making a brand new deep learning model, but we just use a given deep learning model. But running the model frequently causes significant battery consumption, right? Because these edge devices are battery powered, and battery are running out, then it's bad. And nobody wants to consume all of the smartphone's battery just for running these deep neural network models, but because smartphones are not mainly for this deep neural network, but for our daily life, right? So battery consumption should be minimized. So we want to execute these deep learning networks only when necessary. And we want to use other lightweight techniques, maybe conventional signal processing techniques, otherwise, if running deep learning model is not necessary. So for example, we can ask this question: should we execute a heavy object detection deep learning model for every single image of a video, even when the object does not move at all? So if our goal is augmented reality application, which needs detect and tracking all the objects on the smartphone screen in real time, then should we execute the heavy object detection model for every single image of the video? Maybe not, right? So instead of running heavy object detection model for this new image, for a new given image, maybe it is more useful to just reuse previous detection result, right? Just we can reuse and copy the result and reuse the result for the current image. That's enough because the object does not move at all, right? So to this end, we need to design a control logic to decide when to execute a deep learning model, which should be also simple. Because if control logic is heavy, there's no point to execute deep learning model less frequently because control logic itself is heavy already, right? So logic should be simple, and with this simple logic, the deep learning model should be executed far less frequently. And another area is resource utilization. Basically, now these guys yell that, we do have various computing resources, even though our resources are constrained, but we do have various computing resources, including CPU, GPU, and even TPU sometimes. So, and sometimes these days, the tasks that should be run at the edge devices, it's getting heavier and heavier. So sometimes edge devices should run multiple deep learning models at the same time. So it is very important to use what kind of resources for what task and when. By utilizing these resources efficiently, maybe the latency can be reduced significantly. And simultaneously, we should not forget that we have still powerful cloud computers here, right? Don't forget me. And so utilizing cloud and edge computers synergistically is another valuable research topic to investigate. For example, light and latency sensitive tasks may be good to be computed on the edge, while heavy and latency tolerant tasks need to be computed on the cloud, so that users do not sense anything wrong. And this is what I did maybe 4 years ago, before smartphone started having GPU. So smartphone just used CPU and could not compute a heavy task, and it offloads a lot of heavy tasks to the cloud. But still, users cannot sense if the cloud is running this heavy computation or the smartphone is running this heavy computation. So now on-device distributed learning. So even though performing inference, so far I talked about performing inference, not training on a local device, right? So on a local device can protect privacy. Performing inference on a local device can protect privacy, but to train a model, we still need training data at the server. This means that even though inference is done locally, the server still needs to gather big data set, maybe private data set for training the model, which also causes privacy leak. It would be even better if users don't have to share their private data at all, even during the training phase, right? So these devices don't want to share data with the server, even for training, not just for inference. To this end, a relatively new field called federated learning is fast growing these days. With federated learning, data is born at the edge and lives at the edge until it dies. So if data lives and dies completely locally and not shared with anyone. So in brief, so how the federated learning goes, in brief, the server generates a global model and it shares the global model with local clients which participate in the training process. And once the global model is given, each client trains the model locally by using its own data, not centralized data, but its own data. And then there'll be like n types of different locally optimized model. And this client sent this optimized model to the server. And the server aggregates all these differently optimized models and generates, based on these n different locally optimized models, it generates a global model. It updates a more accurate global model. Maybe just by averaging all the weights of the different locally model. This is called FedAv, of the very first algorithm in federated learning. But magically, it just works. By averaging all these weights, global models' performance is improved gradually. It's kind of interesting, right? Yeah, so far I've been introducing a lot of research topics, and now actually another interesting area is meta learning, but I'd like to skip that part because as Professor Tae-Seok Kim already gave a full presentation only dedicated to meta learning. So next, let me briefly introduce what our lab members have been doing in the ambient AI field. First of all, we constructed a testbed for ambient AI comprising tens of smart edge devices. So in the left figure, you can see Google Coral devices, which have edge TPU and mobile GPU. And in the right figure, you can see some Jetson Nano series, which have mobile GPU and actually more computing resources compared to Google Coral. And you can see here some RGBD cameras and LiDAR sensors here. And in terms of research, first, let me introduce some application-oriented research. Some of my students are interested in healthcare, specifically sleep, which directly impacts our physical and mental health together. So we collaborate with Professor Hyung-Sin in the School of Medicine and try to extract sleep-related information such as sleep stage, REM sleep, N1 sleep, and so forth. And also respiration status while sleeping by using brainwave or sometimes video, which is much more challenging. So you might imagine, sleep stage classification only using a video is quite challenging, but because you can see their face and the whole body is covered by a blanket. So what can we extract from this video, right? But our idea is basically focusing on the stomach movement, might be helpful. So we'll see how it will go. That's our hope. And next item is floating population estimation using electric scooters. So the idea is that let's deploy a low power camera on an electric scooter, and using this on-device camera and resource constrained microcontroller, let's count the number of people in a taken image, right? And there are numerous electric scooters in the city. And by gathering the number of people information from each electric scooters, maybe we can have some floating population map, which KT or SKT provides by using smartphone-based information. And the challenge here is to run a crowd counting model, we need to squeeze this model extremely to run this model on sub-megabyte microcontroller, which is quite challenging. So we'll see how it goes. But there are some recent techniques that we can apply. Basically, neural architecture search-based approach can squeeze a model, vision-based model, quite significantly. And there's an example of a model running at a sub-megabyte microcontroller, actually. So looking at this result, we have hope to proceed. And regarding lightweight execution, one research recently got accepted from a conference with my master's. And this is about a mobile app that generates test script automatically for quality assurance process. So once you draw a test scenario on a smartphone screen, rather than manually typing and generating test script, you will see just automatically converted test script from this mobile app. So software developers do not have to write test scripts manually. So, and because it should run on device, a fast execution is the one we should achieve. So as I said before, we wanted to use execute DNN as less as possible. And we mix this DNN operation with some lightweight traditional signal processing techniques. And as for model lightning and resource utilization, we have been trying to enable on-device 3D object detection, not 2D, but 3D, which is challenging because, as you know, a 3D object detection model is quite heavy and takes a long time to run on edge device. So our approach is to modify both deep learning model and system execution, so which creates synergy to significantly reduce inference latency without sacrificing accuracy. So we are using Jetson Nano, as you can see here. And in the realm of on-device learning, a student investigated personalized federated learning, which is literally to generate a personalized model for each user rather than applying a single global model to all users. So it is closely related to meta learning, and yeah, the paper is submitted, and we are waiting for some good news. We'll see. And another research was semi-supervised federated learning. The motivation is that users never want to label their own data, right? And sometimes users do not have enough expertise to label. So it is not practical to assume that all the data is labeled in the federated learning scenario. So we change the scenario a little bit. So users have very few labeled data, and most of the data are unlabeled. And what we can do to do federated learning more efficiently. And yeah, we submitted one paper in this research. Yeah, and now some fun time, hopefully. So I've been teaching the Ambient AI platforms and practice class, and there are some class projects, and I require to submit demo for each project. So let's see what students have been doing so far. So the first thing is, yeah, so one student has some bad motivation. he wanna get money, a lot of money, with the help of AI technique. So this demo is playing poker using augmented reality. And let's play the demo. So this guy wear HoloLens on and play a poker game with the computer. And by using object detection model, the HoloLens captures this image and see what type of cards are on the screen. And based on the you can see all this card type, right? And by using reinforcement learning, the program guides the user what kind of card he should hold, right? And if the estimated score is high, then he will get more credit. Yeah, this is how it works. But yeah, this is just prototype. I'm not sure if it is really working in practice, but we'll see. And another application is the motivation is to avoid COVID-19. But yeah, the COVID-19 might disappear soon, so I'm not sure if this application will be useful or not, but let's see the demo. Sorry. All right. So next application is real-time face filtering. The motivation was that there are a lot of like personal broadcasts by using YouTube, Africa, whatever, right? And there are a lot of pedestrians around the main character. Then they don't want to expose their privacy, right? Just by passing, due to the fact that they just pass the camera, right? So based on the Edge device, the app of detect all the faces and recognize the faces and remove all the irrelevant faces. That's the goal. So these guys are main and other faces should be filtered out. And next application is for children. So children are always in danger, even at home, because they want to climb and climb and climb. I'm also raising my kid. Yeah, she's always in danger. So how about detecting some dangerous situation when a child climbs up, right? So technically, it extracts a body key point and estimates its pose. So it's not detect the movement, but it detects pose like this, then warns. And also, yeah, there was a trendy class project due to the fact that law regarding electronic scooter suddenly became more strict in the last year, 2021. So how about detecting helmet based on vision, smartphone camera, and also how about detecting what kind of road the users are driving on, right? Pedestrian road or because the road condition is different, some vibration patterns are different. So that can be, by using the vibration pattern, the road type can be classified in a very lightweight way, not even using a deep learning model, just classical machine learning model. And lastly, also there have been a lot of reports that drivers do lots of things that they should not do while driving, right? Yeah, they are sometimes talk through the smartphone, and actually these guys are doing multiple tasks simultaneously, which is very dangerous. So how about detecting these dangerous students and give some alarm to the driver so that he can focus on driving? So it's infrared camera based pulse detection. So you can see a lot of labels here. Top right, adjust radio, a drink, reaching behind, drive safe. Yeah, even hair and makeup. So a lot of labels you can see here. Actually, she is not driving, she tends to drive in a parking lot. So it is not actually dangerous, but yeah, for experiments, it is enough, I think. Yeah, and this is the very last slide. Wait, what happened? Sorry. This is the very last slide. Our grad school is actually thinking about some event about ambient AI. It's called Ambient AI contest. So how about, yeah, making some cool things using ambient AI devices. So for this event, actually Google donated 100 Cora boards and they are on the way. So if you are interested, and just stay focused on, and there will be some announcements sometime in the future. Thanks. Yeah, if you have any questions, yeah, just feel free to contact me. I'm in 416 and this is my email. Thank you.